The title is Open Problems in Polyhedral Combinatorics. I feel justified to speak about that on the meeting for the Hungarian method, because polyhedral combinatorics is really the offspring of the Hungarian method. And even if you go back to the original paper, one of the two originators, I should say maybe one of the three next to Harold and König, Eggervari, already he gave a min-max relation for the maximum weight, perfect matching in complete by that graph. You can see that as the first result in polyhedral combinatorics. Maybe I can see this other projector. It's in Hungarian, but one thing if you don't know Hungarian, you will recognize here, there is a min-max relation here. And you will also see that it is a min-max relation using numbers, variables, the A of A. And here is the min-max relation for the maximum weight of perfect matching in a complete bipolar graph. Different from what Penalty has told, here is something about the non-negative, negative. I mean, even if you don't know Hungarian, probably you know that non-negative. But the point is that he also restricts himself to the weights being non-negative. Then negative refers to the weights being non-negative, and then you can restrict yourself to non-negative dual variables, because then the maximum weight is equal to the maximum perfect weight in the moving diagram. Well, you can easily understand that. Harold just told that he hardly knows Hungarian, but he's very modest as usual. In this paper, he said the following. Well, I tried to learn Hungarian for 25 years now, and I didn't succeed, but here. I then spent 2 weeks learning Hungarian and translated the paper. It's very impressive. Well, and that translation is, of course, very useful. I think it's the only translation of that paper. Papers of König had usually been translated into German. There was always a German parallel journal with translations of Hungarian papers, but this was from the Mathematica Lato, and I don't think that had other translation. So I think this is the only translation of the Eggervari paper. It's in a report. It's never been published, Harold. No. So it's in I found it in the Fine Library. Maybe in a few other libraries we have it. And if you read it, it's a very useful translation. You read, as Harold also told, it's very algorithmic already. I mean, the word algorithm doesn't occur in it, but there's a kind of a step in it, which you can, if you know about algorithms, you see, oh yeah, that you can do something algorithmic with it. At that time, the notion of an algorithm was not existing. I find it interesting to give another paper here, which is from 1946, from Easterfield, which also gives an algorithm for the assignment problem in 1946. And the algorithm also has a reduction to perfect matching, to non-weighted perfect matching. He called it an algorithm because it was better than finite. At the time, anything better than complete enumeration, better than n factorial, was considered to be an algorithm. And he said, well, this is an algorithm. I like very much his footnote, because he did it for the demobilization of the Royal Air Force area. But he said, unfortunately, the unexpected ending of the Japanese War prevented the implications of this approach from being worked out in time for effective use. Probably in a very ineffective way, this demobilization. station. But it's better just came too late. We found it. Another paper also attempting to solve the assignment problem, and that relates to what is an algorithm. People thought you have the assignment problem, differentiation problem, it's about the same. If you do it in the matrix terminology, shift this because there's one important thing. If you calculate the complexity of this infinite field algorithm, it is to the power n squared. It is faster than n factorial. So it's better than finite, better than complete enumeration. And what this next paper does, what I will show now, is by Julia Robinson on the Hamiltonian game, a traveling salesman problem. I think it's the first paper ever using the word traveling salesman problem. And in an unsuccessful attempt to solve the traveling salesman problem, see first stage, the purpose of this note is to give the method for solving a problem related to the traveling salesman problem. Later on she says that here, an unsuccessful attempt she speaks about to solve the TSP, she comes to solving the assignment problem. She makes already one important observation, that just the number of solutions is not a measure for the complexity of the problem. However, at first glance it looks more difficult, the assignment problem, than the traveling salesman problem, for there are obviously many more systems of circuits than circuits. A system of circuits in a bipartite graph or in the matrix corresponds to an assignment, and a circuit corresponds to a Hamiltonian circuit here. So she observes here that the number of solutions is not a measure for the complexity, and she believes that it would be feasible to apply the method, the cycle cancelling method. She finds for optimum assignment would be feasible to apply to as many as 50 points, provided suitable calculating equivalent time is available. I think later on this type of methods has been used quite often for the transportation problem, for mean cost flow, mean cost circulation, and indeed cycle cancelling methods. Finding a dual solution and then finding a negative cycle, improving the solution, and that iteration is basic in many further developments. But then Harold Q found in 1955 a Hungarian method. This paper. I think it's pioneering in many respects. It is the first polynomial time method. At least it's the first method which is really stated to be polynomial time. Actually, Harold did not mention it himself in the paper, I think. He didn't make a complexity analysis of the algorithm, but later James Munkres, he did that, and he really gave a polynomial. I mean usually when people make estimates, they just put an O sign and some n in the power, n and some power, but here really this polynomial for the number of steps. He says the number of steps is n to the power 3, but actually the complexity is n to the power 4 because he takes scanning a line, here, scanning a line as one operation, so going along a whole line of a matrix, but it takes n steps, of course, if you do it just in the usual models of computation. So you get all n to the power 4, but he really gave a polynomial. There were of course already earlier polynomial methods like the minimum spanning tree algorithm. It was polynomial, but it was trivially polynomial because the number of, it was trivially an efficient method, so it wasn't observed in that paper. I forgot the name of the Czech guy. Borówka, yes, Borówka. It's also pioneered in the sense that I think it's the first primal dual algorithm, where the primal dual iteration is explored and especially for combinatorics, in combinatorics. I mean, of course, for LP you could say steepest descent is maybe already a primal dual algorithm, but applied application of primal dual algorithms in combinatorial optimization, this paper might refer. And also what is basic is that the iteration is an iterative shortest path search. You find the shortest path, you improve the solution, you find again the shortest path in some derived graph, you find a better solution, and this way you find better and better solutions. And this idea has been the basic for many further developments in combinatorial algorithms, say for Riemann flow and also in matroid intersection, for direct cuts you can, there are algorithms based on this. So this is a very basic idea which I think was pioneered in this paper. And as I mentioned, it forms the basis for a whole theory, and it's, the offspring of it is my book. My talk is about open problems in polyhedral combinatorics, but I take many problems from this book, so you can find more background in the book. It's not expensive, €90. Well, sometimes people, I had once an interview for some technical journal, and they said, well, now you've written that book, all problems are solved. And you might think, well, almost main problems are solved, but there is one main problem which is not solved. Anybody has an idea? What is the main problem which is not solved?
T equal NP.
Yes, precisely. This is of course the basic problem. I mean, it is basic in many other areas, complexity theory. It's also basic in polyhedral combinatorics. If NP would be equal to P, you would have a whole range of further polyhedra to be investigated. And well, if NP is not equal to P, then maybe we have a way to really go to the kernel of the problem. I mean, we really don't know why, say, the traffic sensor problem is difficult. That is a completely different technique actually than proving that something is easy. So there are a few clues maybe, but there is not really a theory which already proves that the traffic sensor problem is difficult. That there is no polynomial time algorithm for that. And that is the basic issue there. And if there would be a proof of that, hopefully you can get easily to the kernel of such a problem. You know why it is difficult, so you know maybe the direction towards the kernel of the problem, and maybe it tells you also something about why the polyhedra. I mean, I didn't say that yet, but there is the Elmquist method. It says that there is a polynomial time algorithm for a certain combinatorial problem, even only if the associated polyhedron is well associated polytope is well described. I will not go into the technicalities of that, but there is a big relation between polynomial time solvability and the fact that facets of the corresponding polyhedra polytopes are known. This already in the early papers of Dirk Ekman says complexity of the problem and the polyhedra associated are related. If this problem would be solved, if NP is P, which not many people believe, but if that would be the case, then you have a big sea of further theorems to find in polyhedral combinatorics. Well, my second is just more down to earth. It's can a maximum flow be found in order and time? In the book I have some tables, and this table gives the second part of the table, but these are among the best complexities you have for maximum flow. N is the number of vertices, n the number of edges, and it's quite close to order n m. And those algorithms are quite complicated. They use a lot of data structures. So somehow my question is also not only is there an algorithm which works in order n and time, but is there also a simple one? I mean, you would expect if it's order n and time, there's a simple algorithm for that. But somehow nobody knows how to do that. Maybe just around the corner.
Like, would you like to ask a question?
Yeah, sure.
Why not order m time? Can a maximum flow time in order m?
In order n, just order n, yeah, why not? Order n is that's too small, right? Yeah, I agree. But if this problem is be solved, then that would be my next question, of course. Yeah, shortest path can often be found in order n time, but not known at least. So, yeah, that's. I just ask it because it's close to this. But you believe there is an order n algorithm?
Well, I would be happy to put some logs on it for data structures. That would
Oh,
bother
yeah.
me as much as the mn bothers me over here.
Yeah. Okay, so that's a good question. Now this question is already around for a long time. Is the matching polytope the reaction of the polytope? This polytope is the number of atoms. Everybody knows the famous characterization by Jack of the matching polytope, which requires an exponential number of facets, which is not bad for complexity actually. I mean, you can recognize them all in one time, so nothing bad in that respect. But this is just a very intriguing question. Also because if you would have an answer, maybe you can solve just the matching problem in general graphs, not in micro graphs, but in general graphs, by the simplex method. Then you just throw it into simplex or any other system, and you get your matching. Well, this is what do the experts think? Is it yes or no?
Maybe.
Maybe. Be careful. Now, this is a more favorite question of the projectile Boodle from 1978. Is the minimum size of the directed cut in the directed graph equal to the maximum number of disjoint directed cut covers? Maybe I should give a little explanation. If you have a directed graph, then the directed cut is obtained by splitting the graph into two parts. And if only arcs go from this part to that part, you call the set of arcs there a directed cut. And the directed cut cover is just a set of arcs that intersect every directed cut. There is the well-known Lucchesi-Jankel theorem saying that the minimum size of the directed cut cover is equal to the maximum number of disjoint directed cuts. And the question of Boodle, projectile Boodle, is you can change the terms directed cut and directed cut covers. Like you can do in many theorems of Koenig. The maximum matching in a bipolar graph theorem of Koenig. If you it's a min-max relation of this type, and if you exchange the two terms, you get again a valid theorem. And also in Menger's theorem, you can do it. The minimum size of a cut is equal to the maximum number of paths for x to t, and if you change cut, well, I can say that wrong probably, but in the Menger case, the cut separating 2 points and the paths connecting 2 points are dual in this respect. Like here, directed cuts and directed cut covers. There is a weighted extension of that, which is not true. And usually for most theorems, like the Koenig theorem can be extended to the weighted case of Egervari. As soon as you have a combinatorial case, a cardinality case, you can extend it to a weighted case. But the weighted extension of this is true, the weighted extension of this is not true. So that is a little bit non-promising. The problem with proving here is that direct cuts, the meaning of direct cut changes if you take out an arc. If you would like to apply induction, you take out an arc, then you can create new directed cuts. For instance, if the red arc was there and you take it out, then first that was not a directed cut, and after that it is a directed cut. So the usual induction tricks don't work there. It seems. Now the next question or problem. Give a combinatorial problem time algorithm for finding a maximum stable set in a perfect graph. With Martin Goethe and Patkilovas, we found that there is problem, an algorithm for this, but it uses the elephant method and semi-definite programming. So it's not really combinatorial, and with the new developments in on perfect graphs, and strong perfect graph theorem being proved, correctly being proved, and also you can recognize a perfect graph in polynomial time now. So this is one of the open problems there. People like Maria Tudowski and Paul Seymour working on this type of questions, they also don't see how to solve this. So they have a huge box of tools now for studying perfect graphs, but still this problem remains unsettled. And the last one is also more favorite. Actually, I was just discussing this with Jack about theorems where fatal cuts are used. Maybe people know that it means that you make some combination of inequalities and then you round the right hand side and you get a new cut for, say, A01 for example. And somehow we were discussing are matchings the only area where this can be applied. Matchings, B-matchings, generalization matchings. And maybe this is a good candidate for I will explain what it means with MAD and T-paths. If you have an undirected graph and a subset T of the vertex set, then a T-path is a path that connects two distinct vertices of T. And then Mader gave, in 1978, a bimaxillation, the maximum number of internally disjoint T-paths, so disjoint except for the endpoints. The endpoints may be disjoint, but they need not be disjoint. Is equal to a minimum of some complicated formula, which I don't give. It wouldn't help very much if we see it for the first time here, and if you know it, I don't need to give it. But this is just known for the cardinality case, and it's not clear what should be the weighted case. Like the Egger-Vari is the weighted case of the König theorem. So what would be the right extensions? There are several developments here. I mean, there are polyhedral aspects. There is a paper by Keizer, Pendeving, and Stauffi who use LP duality to derive with the elephant method a polynomial time algorithm for the edge-joint version of this. There's also an edge-joint version. That's of Mader. You can derive it from the vertex-joint version, and it is a little easier, and you can then translate this into a min-max relation in the flavor of an LP duality. And using this LP duality in the elephant method, they could prove that you can find this maximum number of internally edge-joint T-paths. So, but I don't see how to extend that to the weighted case and how to extend it to the vertex-joint case. Now there are algorithmic questions around there. Recently, I mean, the old algorithm of Latzi, the Lovas, based on matrix matching, finding this maximum number of internally disjoint T-paths. recently there was an algebraic extension given of that theorem, and I think Chudnovsky, Cunningham, Deal found an algorithm, column 10 algorithm, but it was, in a sense, well, I don't want to diminish your work, of course, but it is a little bit brute force, column 10 algorithm. You collect a lot of matchings, matrix matchings, in that, and you keep a long list of them, and you try to find a new one or a bigger one. And if you find a new one, you know more about the structure, and finally you can say, well, there is no bigger one, so we have the biggest one. So it is not so much in the way of an iteration which extends a given matching in a primal dual fashion. It is, if you really look at it, but also this algorithm I was mentioning of Chudnovsky, Cunningham, and Gielen has the same phenomenon, that they create a long list. Now the last aspect is there are many matrixal aspects. You can I gave a short proof of Mader's theorem, and you can see that you can derive always a matroid out of it, like you can make out of matchings a matroid. You can extend it to making matroids out of that, and maybe the relation with matroids gives you some more idea to solve that. There are also recent results by André Schrijver and Lassie Seger and Jula Papa. I think, I don't know whether they will speak about this, but they are also related to this. Okay, this is the last problem. There are many more long problems in my book, but I will be happy if any of these or any of the book will be solved. Thank you. Yes, that is of course, I mean that should, after NP is not P, that I consider that as the most important problem in this area, but it's not so really polyhedral combinatorics, I find. It's polyhedral. I mean, it's basic problem in polyhedral. Yeah. So what I mentioned in my book, it's not, so the Hershey reactor certainly is
It's on the combinatorics of polyhedra rather than on the polyhedra of combinatorics.
Yeah, but it's directly. I mean, it's
Question? Nice.